Okay, take your attendance. Okay, class, today we will be starting a new topic. Okay, the quantum physics we done last class. So as usual, try to do the passes. Okay, and exam made questions. Try to get the idea. Okay, how it goes about. Okay, so we start. So today we will be going for the next topic. So the next topic is going to be nuclear physics. It's going to be nuclear physics. Okay, so we'll be discussing nuclear physics today. So altogether got 15. So after this, we got another 2 to go. Okay, so without wasting time, so let's continue. Okay, nuclear physics is actually you learn half of the nuclear physics in AS. Okay, you learn about the Rutherford experiment, how the atomic structure was developed, until you talked about the what do you call the quarks. Okay, what is the fundamental of particles? We talked about that. Okay, this in A2 we're going to talk about something called binding energy. We're going to talk about binding energy and talk about radioactivity, even depth in depth. Okay, like half-life and everything we're going to discuss here. Okay, I know O levels you learn about half-life, but here we go more as usual. That's what happens to other topics. We will go in depth to the formulas and everything. Okay. Yeah, of course. This formula is nuclear means E equals to mc squared, right? So Einstein introduced. He tells that mass and energy are interchangeable. Okay, the only scientist who said that. Okay, mass can convert to energy and energy can convert to mass. So E equals to mc squared is a formula is used for what? To find how much of mass equivalent to how much of energy. Okay, and the mass is converted to destroyed to become energy. Yeah. So when that happened, when mass destroyed to become energy or energy changed to mass, when mainly when the mass is like disappears, it happens of course in the nuclear level. Okay, at the nuclear stage, right? At the nuclear stage it happens. So of course, nuclear reaction got two type, right? Fusion and fission. So fusion and fission, the mass is destroyed. I believe you heard about this too before, right? Fusion, fission. Okay, fusion, when two lighter nuclei combine to form a heavy nucleus and releases energy. It's fusion, right? Two lighter nuclei, okay, combine to form a heavy nucleus and releases energy, right? Fission. Oh, sorry. Yeah. Sorry. Yeah, correct. True. Fission. The split of heavy nucleus to two or more lighter nuclei and releases energy. That's a fission, right? I think by using a neutron, normally we use neutron, okay, to do fission. Okay, so when a nucleus form or nucleus is tend to become nucleon, they change. Some mass is changing. That mass called mass excess. Okay, when a proton neutron come together to form a nucleus, the mass of the nucleus is less than the sum of the masses of separated proton neutron. Okay, so what is the meaning of that? Let's say we go for helium. Okay, what is helium? Helium is 42, right? Helium 42. Helium made of 2 proton and 2 neutron, right? 2 proton, 2 neutron. Okay, so there are 4 nucleons. Okay, when the 4 nucleons combine form a helium, they found that the mass of the helium is slightly smaller than the mass of the 4 nucleons. So there is some mass difference happen. Okay, the mass difference is called mass excess. Okay, this difference mass is called mass excess, or sometimes we call mass defect. Okay, mass excess or mass defect of the nucleus. Okay, so the mass excess or defect is actually the mass of the separated protons, total nucleons, minus the mass of the nucleus is your mass defect. Differences in the mass. Okay, yeah. So this is the formula. The Z is the what do you call the proton number of protons, mass of the protons plus mass of the neutron minus the mass of the nucleus will give you the mass defect. Okay. So before we continue about the mass defect, let's get to know the unit for masses when it comes to nuclear stage. When atomic stage, we know mass is kilogram. But when it comes to subatomic particle, the mass is too small. So we use atomic mass unit, right? Unified atomic mass unit. So atomic mass unit is 1U. What is 1U? What is atomic mass unit? It's defined as being equal to the 1/12 of the mass of a carbon-12 atom. Remember the definition. In exam they'll ask, what is meant by 1U? 1U defined as the mass of mass that equivalent to the mass of 1/12 of the mass of a carbon-12 atom. Okay, it's 1U. I believe you learned this in chemistry. Okay, 1/12 of carbon-12 atom is equivalent to 1U. Okay, so 1U, you know, in the front page is 1.66 times 10⁻⁻27 kilogram. Yes, 1U. So all the subatomic particle mass is written in terms of U. So for example, you see here proton mass, neutron mass, electron mass. Proton mass. Last time in your O levels, what is the proton mass? You normally take like as 1 unit. 1 unit is actually 1U. 1U. Okay, neutron also is like mass is 1U. Mass of electron is very small. A fraction of U, very small fraction. So this is what you learn in O levels. 1U. Okay. Even AS also mass of proton. Just we go to the front page, check how much the mass of the proton given, right? But for nuclear lab, in this topic, we will give you the mass of the proton in terms of 6 decimal or 5 or 6 decimal places. When you go for mass for 5 or 6 decimal places, you can see that for the first time, the mass of the proton and mass of the neutron is slightly different. Okay, which is more massive? I don't know how many of you realize this. Neutron is slightly more massive than proton. Okay, neutron is slightly more massive than proton. Okay, so 1.008665. These values you don't need to memorize. If in the exam, if they want you to calculate, you need the mass of that substance in 6 decimal places. They will give you. Okay, yeah. So this mass of this subatomic particle. Okay, they will give 6 decimal places. Okay. So why they give 6 decimal places here? Just for the sake of finding the mass defect. Just to find the mass defect. Okay, when the nucleus is formed. Okay, for example, we go one example. This is one example. You see this question here? Calculate the mass defect for a carbon 14. Okay. The measured mass of the carbon 14 nucleus is found to be 14.003240 U. This is the mass of the nucleus after the mass is formed. After the nucleus is formed, the mass found to be 14.003240. So calculate the mass defect first. So how are you going to find the mass defect? Mass defect is total mass of the nucleon minus the nucleus mass, right? So carbon got how many proton, how many neutron? Of course, he got 6 proton. He got 6 proton plus he got 14 minus 6. How much? 8. He got 8 neutron. So the mass of 6 proton plus 8 neutron minus the mass of the nucleus will give you the mass defect. But the mass of the proton and neutron, we don't go for 1 decimal place. We go for 6 decimal places, like given earlier. The proton, 6 decimal places. So we get the mass defect. Okay. So yes, this should be the working, the first part. Okay. So how to find the mass defect? So the total mass of the nucleons minus the mass of the nucleus. So this is the mass difference between the nucleus and the nucleons. Okay. Okay, now next. Calculate also the energy equivalent of this mass loss in EV. Okay, they're asking this mass, the mass defects, this amount of mass defects is equal to how much of energy? How much of energy? Equal to how much of energy? According to Einstein, mass is energy. Right? Is mass can convert to energy. So that mass is how much of energy? So of course we use the only formula we know is E equals to mc squared to calculate the energy of a certain mass. So we use the mass is 0.109736 U. So you need to multiply by U, the 1.66 times 10⁻27. Of course, when you use this formula, you have to use the mass in kilogram. Kilogram. Multiply by the speed of light square. Of course, C, speed of light. So you'll get answer in joule, because they want in EV. So divided by 1.6 times 10⁻⁻19, you get in EV. So under 2 mega EV of energy will be released equivalent. This energy is the energy equivalent to this mass. If this amount of mass destroyed, this amount of energy will be released. Okay. So this is the first idea, mass defect. We never heard this before. Okay. When the nucleus is formed, the mass of the nucleus was different than the total mass of the nucleons. Okay, there is some differences. Okay, So the differences of the mass of the nucleon and the nucleus is called mass defect. Okay. Any questions so far? No questions. Okay. Okay, now as we go to one important term called binding energy. Yeah. Okay. So binding energy. Okay. What is meant by binding energy? So the fourth point is the definition for binding energy. Okay. So let's immediately go for the fourth point first. What is binding energy? Binding energy is defined as the energy required to completely separate the nucleon of a nucleus. Please add to infinity. Guys, please add this to infinity. What is binding energy? The amount of energy required to completely separate the nucleon of a nucleus to infinity. That's binding energy of the nucleus. Okay. So before that, you see the first point. Within the nucleus, there are strong forces which bind the proton and neutron, of course, right? You know, in the nucleus, the proton and neutron are as a strong nuclear, what do you call? Nuclear force. Okay, strong nuclear force. Okay, they are binded together. Okay, you want to separate them like helium. Helium got two proton, two neutron, what? Two neutron, two proton. You want to separate them. Of course, you need to overcome that the force between them, right? Which is very strong. So that the amount of work need to be done, the amount of energy required to separate all this proton to infinite is called the binding energy of that nucleus. Okay, binding energy of the nucleus. Yeah. So scientists found that the binding energy of the nucleus is actually is equivalent to the energy of the mass defect. The energy of the mass defect is the binding energy of the nucleus. So that's what has been discovered. Okay, means what? I go back early. Just now carbon. Just now carbon 14. Just now we calculated the mass defect of carbon 14, and we found the energy is 102 mega eV, and this is the binding energy of the carbon 14. Okay, 102 is actually energy of the mass defect. This is the binding energy of the carbon 14. Okay. Yeah. So try to understand the last 2 points. What is binding energy means? The amount of energy required to completely separate the nucleus of a nucleus. Okay. Yeah. So if the nucleus got more nucleons, okay, like uranium, right? Uranium is the nucleon number is more 200 over, right? So you've got more 200 over nucleons. When you want to separate them, all of them to infinite, the binding energy will be greater. You have more binding energy for the uranium because more number of nucleus, the particle, the nucleus as for uranium. Okay. So remember the definition. What is binding energy? The amount of energy required to completely separate all the nucleons to infinity. To infinity. Okay, let's explore more about this binding energy. Okay. When separated nucleons combine to form a nucleus, there is a reduction of mass, equivalent amount of binding energy is released. Yeah, correct. See here, to dismantle the helium, you separate all the 4 protons. Let's say the amount of energy required, let's say 100 mega eV. To merge these 4, to form this nucleus back by combining these 4 again. The amount of energy required also is 100 mega eV. Okay, 100 mega eV. When you want to split, let's say the nucleus is stable nucleus. Okay. I go to the whiteboard just for a while. Okay. Let's say you have a stable nucleus. You have a stable nucleus made of 4 helium, normally stable one. Let's say helium stable. It's stable, right? So helium nucleus, when split into split them. Okay, split the nucleus. What happened? Energy will be what do you call? Absorbed. The energy will be absorbed. Will be absorbed. Okay, absorbed. So energy will be absorbed from the surrounding to form this 4 nucleons. Okay, for stable. So energy absorbed. Let's say the binding energy is 100 mega eV. The binding energy, so 100 mega eV will be absorbed. Okay, when these four nucleons form the nucleus back, the will be released. Okay. So you see, for stable, this is only for the stable nucleus. Correct, right? Let's say 4 nucleus has a greater mass. It's a greater mass compared to the nucleus. Okay. When the 4 nucleons merge, the mass is decreased. The mass drop. Okay. The mass will drop. Okay. When the mass drop, what happened? Energy will be released. Energy will be released. Okay, energy will be released. So when the subatomic particle combine to form the nucleus, energy will be released. Okay. When the nucleus split into the nucleon, energy will be absorbed. Okay. Of course, you want to dismantle a stable arrangement. You have to do work. You supply energy to break them. Okay. And when they will form by themselves naturally. Okay. So this is for the only for stable nucleus. Stable nucleus. Okay, that's what this sorry. That's what this slide does. This slide. When separated nucleon combine to form the nucleus, there is a reduction of mass. An equivalent amount of binding energy is released. Okay. This is only happen for stable nucleus. For a stable nucleus. Yeah. Okay. So now I will tell you. I ask you one question. Go to the whiteboard. You see, you have carbon 14. You have uranium 235. Let's say uranium 235. Let's say 235. Uranium 235. Nucleon number. The carbon is just 14 occupants, 14 nucleons, and uranium is so huge with 235 nucleons. Okay. Okay. So carbon and uranium. Can you tell me which will have more binding energy? Which would have more binding energy? Carbon 14 will have more binding energy, or uranium 235 will have more binding energy? Come on, guys. Which one? Of course, the one more nucleons most likely will have more binding energy, right? Right? Because what is binding energy means? What is meant by binding energy? The amount of energy required to separate all the nucleons to infinite. I think to dismantle 235 nucleons, you need lots of energy. Okay. So confirm, uranium will have a greater binding energy than carbon 14. Carbon 14. Okay. But is that means greater binding energy means is that means the particle, is it stable? Is it stable? Greater binding energy means is it more stable? Is it uranium more stable than carbon? let's say carbon 12, let's say helium 4. Is it uranium more stable than helium? Not necessary, right? So binding energy greater means not necessary. The nucleus is more stable. Okay. Then how to check stability of the nucleus? To check the stability of the nucleus, we need to find not binding energy. Of course, we need to find the binding energy, but we need to count binding energy per nucleon. Per nucleon. We need to find the binding energy per nucleon. Each nucleon, how much of binding energy it possesses, that determines stability. Okay, what? Binding energy per nucleon determines the stability. Of course, binding energy of carbon 14 is small. Let's say 200 mega eV. Uranium might have binding energy of, let's say, 1000 mega eV. Okay, let's say. Okay, this is the binding energy for carbon and uranium, let's say. But if you find binding energy per nucleon for carbon 200 divided by 14 and uranium 1000 divided by 235, definitely the carbon 14 will have a greater binding energy per nucleon. Okay, so greater binding energy per nucleon means that nucleus is more stable. Okay, so that's what we're going to do now. Binding energy per nucleon. Okay, so binding energy per nucleon is the total binding energy of the nucleus divided by the total number of nucleons. So binding energy per nucleon is, of course, total binding energy divided by the number of nucleons. It gives you joule per nucleon. So this quantity measures the stability of the nucleus. Okay. So a nucleus which has the greatest binding energy per nucleon will be the most stable nucleus. No doubt about that. Okay. So yeah. So this is check the stability of the nucleus. Okay, don't get confused with the stability of the nucleus and stability of the atom. Chemistry, you learn stability of the atom. Okay, not stability of the nucleus. Okay, stability of the nucleus. I think this is the first time you come across with the stability of the nucleus. What determines stability of the nucleus is binding energy per nucleon. Okay, how much each nucleon is binded, how much of energy, okay, per nucleon determines the stability. Okay, so you got the idea? Okay, let's try one example. Binding energy. Okay, one question here. Okay, try to figure out how do you go about. I give you 2 minutes. Come on. Just figure out some idea how you're going to go about this question. What formula do you think you use? What are you going to do? What are you going to measure first? Okay, the first one, helium nucleus is represented by the helium 42. We know that. Use the information given below to calculate the mass defect. Okay. So how are you going to find the mass defect? Mass of the nucleus minus the mass of the nucleus, right? I think the details are at the bottom, right? So what you should do, of course, the mass defect is what? 2 times of the mass of the proton, 1.00728. Yeah. Plus with 2 times of the neutron, right? 1.00866. Of course, this you need to multiply with the U, 1.66 times 10 power negative 19, negative 27, sorry. It's also 1.66 times 10 power negative 27. So you get this, the mass defect. Okay. Or you want to leave it as U also can. You don't want to multiply with 1.6 also can. Leave it as U. So changes of mass defect is in terms of U. Yeah. This is the total nucleon minus with the mass of the nucleus. Mass of the nucleus is how much? 4.001504, right? Yeah. So 2 proton plus 2 neutron minus the nucleus mass, you get mass defect. Just leave it as U. No need to multiply by 1.66. U. How many U? Okay, right? So that's the first answer, right? Mass defect. So yeah, the total mass of the 4 nucleons add up is found to be 4.031188. So the nucleus minus the nucleons minus the nucleus gives you the mass defect. In terms of U. Right? Okay. Okay, next. Find binding energy. Binding energy, once you know the mass defect, you can find binding energy, just mc square, right? But the problem is more tedious. The mass have to convert to kilogram, so multiply by 1.66 times 10 power negative 27. Unified atomic mass, and c square has speed of light squared, so you get that. Energy in joule. Energy in joule first. mc squared, the answer is in joule, right? But question once in terms of EV, they never said given in EV. So joule change to EV, just divide by 1.6 times 10 to the power negative 19. So give you in terms of EV. Electron volt. Normally nuclear physics, the energy unit preferably normally they will ask is in form of joule and in form of EV normally. Because we are talking about energy of the subatomic particle. So it's going to be in EV. Okay, so binding energy. So we go back finally, what they ask, binding energy per nucleon. So just binding energy divided by the number of nucleons the helium possess. Of course, it's 4. Take the nucleon number, 4 nucleons. So of course, the 28.4 mega EV divided by 4, we get the binding energy per nucleon. Okay. First question. Okay, try to get familiarized with the idea. How binding energy linked to stability of the nucleus. How mass defect linked to binding energy. How binding energy linked to stability of the nucleus. Okay. Greater binding energy per nucleon means more stable the nucleus. Okay. Yes, please stop me if you have any questions. Okay, so if the class is very silent, so I consider you okay with so far the idea. Okay, let's progress. Okay, so before we go to these questions, yeah. So this is a very important graph you need to know. So scientists found all the mass binding energy per nucleon for all the elements in the periodic table. Okay, they found a very weird graph. Okay, the graph they obtained is like this, going up and come down again. That is a peak value. Okay, so they found that not the smallest nucleus is stable, or not the largest nucleus is stable. The most stable nucleus is found to be in between. Okay, this is the region. The brown region is the most stable region. Okay, and they found iron 56 is the most stable nucleus. Okay, iron 56 is found to be most stable nucleus. Okay, last time you don't know the reason, but now in A2 if they ask why iron 56 is the most stable nucleus, so what's the answer? You must say it has the highest binding energy per nucleon. Okay, iron found to be as the highest binding energy per nucleon. Okay, so that's why it's more stable. You know, iron prone to rust, right? Easy become rust. Iron easy become rust. So the atom is not stable. Of course, the atom is not stable. The electron easily go out and come in. So it easily become ionized. but the nucleus is very stable. Okay, the nucleus, the headquarter, is very stable. Okay, that means nucleus won't transform to any other nucleus. The iron means if you have iron, I think for a long time, billion years also it will be in form of iron and never change. But other elements have chance to the nucleus have chance to convert to a more stable nucleus. Okay, that's what happened to uranium. You see, uranium has a reasonably low binding energy per nucleon, very large nucleus. So why radioactivity happens? First of all, the elements want to achieve stability. So that's why it's transforming to a more smaller, stable nucleus. Okay, that's why uranium exhibit radioactivity. Okay, so the nucleus, which are very huge, normally want to split, become smaller nucleus, so that in the smaller nucleus, the nuclear number will become, mass number will become smaller, or nuclear number will become smaller, so they can go to the more stable region, more stable region. So that's why uranium always does fission process. Okay, fission. Big nucleus does fission. Not instead I say big nucleus, heavy nucleus does fission. The lighter nucleus does fission. They have to merge to achieve stability. Okay. Iron won't fuse with anything. Iron is a very stable. Pointless, it fuse. Okay. If you fuse two iron, I think it's going to transform to unstable nucleus, not a stable nucleus. Okay. Most stable is iron. Okay. Okay, guys, any questions about this fact? Is actually a fact discovered through experiment. Most what do you call stable element is, of course, stable nucleus is iron, because it has the highest binding energy per nucleon. Okay. Okay, this graph not that famous. You can read through, but most important is this graph. Binding energy per nucleon versus mass number. Okay, you have to memorize iron 56 is at the top position. Okay, so more than 56 become less stable, less than 56 also less stable. Okay.
Sir.
Yep.
Hello, sir. Just to confirm, so even though an nucleus has like a high binding energy, it's not necessarily stable, is it? It has to have a high binding energy per nucleon.
Yeah, binding energy per nucleon determines the stability.
Okay, so even if it has the highest binding energy, doesn't mean it's the most stable.
Not necessarily stable.
Okay, thanks, sir.
Okay. Yeah. Okay, so let's move on. Okay. Okay, so yeah. So nuclear fusion, you know this, it happens in where fusion happens, of course, in the sun, right? Sun nuclear fusion. So two hydrogen are merged to form helium and releases tremendous energy. Okay, low mass number may undergo nuclear fusion, as I told you. Smaller nucleuses fuse to form release energy. Final product has more binding energy per nucleon. Yes. So of course, fusion happens, and it's going to produce a more stable nucleus, which has a greater binding energy per nucleon. Okay. Then the reactant, of course, if it has more binding energy, normally it will have a less mass. We will come to that later. Okay. The enormous amount of energy generated in the sun is due to this process, right? Okay, sun give up the energy because of fusion. The fusion happens in the sun is at the core of the sun, not at the surface. So why at the core? Of course, high pressure, very huge pressure and high temperature leads to fusion of hydrogen. Okay, so once our sun, all hydrogen merge to helium. Okay, like not our sun. Let's say you have another stars which are more huge than our star, then even helium in that star will fuse, okay, give up energy, okay, start to fuse. According to theory, they said our sun can't afford to fuse the helium. They only can fuse hydrogen to form helium. Okay. Once all hydrogen turn to become helium, then that's all. That's it. Our sun unable to release any energy further. Okay. Yeah. So the energy release in the fusion process is very much greater than energy release in the fission process. Okay, this a fact to remember. Remember, the energy release in the fusion is always greater than the energy release in the fission. Okay, why? Anybody? Let's say I'm telling you. Let's say you have 1 kilogram of hydrogen used to do fusion. Okay, you have 1 kilogram of uranium is used to do fission. Okay, fission. So finally, the energy released by the hydrogen is greater than the energy released by the fusion. Why? Anybody? Why fusion gives more energy than the fission? The total energy. Because of what? Although both are 1 kilogram of uranium and 1 kilogram of hydrogen, in 1 kilogram of hydrogen, the number of hydrogen nucleus is a lot of hydrogen nucleus. In uranium, the 1 kilogram of uranium, the uranium nucleus is quite big, quite large. Okay, so the number of nucleus in the hydrogen is a lot, right? What is the nuclear number of hydrogen? Is 1U, right? Only 1U. Uranium is 235U. 235 of hydrogen nucleus equivalent to like 1 nucleus of uranium. So because the number of nucleus is a lot, so the amount of reaction fusion happens is a lot, lots of fusion. Okay, so lots of fusion reaction happens per mass. Okay, per mass. The number of fusion occurs per unit mass is greater than the number of fission happens per unit mass. That's why lots of energy release in fusion. Okay, so because of the more number of nucleus, therefore more number of fusion per unit mass lead to greater energy release. Okay. So that's why the idea here, the energy release in the fusion process is very much greater than energy release in the fission process. Okay. So this one example of fusion. So let's say hydrogen changed to helium. Okay. If hydrogen changed to helium, we said definitely helium will have a greater binding energy per nucleon. Helium, if helium is stable, of course, normally the naturally occurring fusion or fission process, okay, will lead to a stable nucleus formation. Okay, so like in the sun is like nature. Okay, hydrogen merged to helium. Of course, helium is a more stable element than hydrogen. So therefore, the binding energy of the binding energy per nucleon of helium definitely is greater than the binding energy per nucleon of hydrogen. Okay, yeah. So there will be energy release. The energy release here we can calculate by using mc squared. By using the mc squared again. But which mass to be used here? In this case, we need to find the total mass of the reactant. We need to find the total mass of the product. The differences in the mass is the one turned to become energy. Okay, so you need to find the mass of the hydrogen, which is something 2 point something 6 decimal places. The 2 mass of the hydrogen minus the mass of the helium, and the neutron also need to be included. The mass, the differences in the mass is the mass which release become energy in this case. We will be doing that, how to find the energy, okay, for this process. Okay, so this is of course fission. You can see the diagram. A neutron was bombarded into uranium, and uranium become unstable mode, and splitting happen. Okay, splits into two small nuclei and releases energy with 3 neutrons. You know this, right? Chain reaction. Okay. Yeah, in general, heavy nucleus disintegrate into lighter, more stable nucleus. The fission fragment have a greater binding energy per nucleon. Yeah. So the product of fission will have a greater binding energy per nucleon. No doubt about that. Okay. More stable. Okay. So you see the process at the bottom here. Neutron get into the 235 uranium, become 236. 236 is a metastable, not a very unstable nucleus, split, okay, to xenon and strontium, and 2 neutrons produced, 2 or 3. Yeah. Okay, so remember, guys, here, tell me if this is the naturally occurring process, fission. Okay, definitely the product is more stable. Okay, in this case, the product is more stable. It's more stable. Naturally occurring process fission. Okay, so more stable means the product has a greater binding energy per nucleon. Okay, greater binding energy per nucleon. But which side do you will have more mass? Which you will have more mass? The reactant will have more mass, or the product will have more mass? Come on, please WhatsApp me if you know. The product will have more mass, or the reactant will have more mass? Which one will have more mass? Okay, I think all of you thinking. You see, when uranium, unstable, okay, react with neutron, produce two subatomic particle. Sorry, two dotted nucleus. Strontium and the other one. Okay, so of course the binding energy and the binding energy per nucleon, here greater than this binding energy, right? Okay, mass of the reactant should be greater than the mass of the product, right? So you should have more mass. The reactant should have more mass. Okay, the reactant will have more mass to the product. Okay, you see here, E equals to mc squared. A very unstable nucleus, okay, when they become stable, producing a new element, the new element will have a small mass. They will have less mass. Okay, so the reactant will have a greater mass than the product. Okay, the differences in this mass, okay, is converted to become energy. Energy is released. Energy will be released. Okay, so remember, when unstable, when unstable become stable nucleus, okay, both the nucleus, remember, mass decreases. Okay, mass decreases. Okay, the mass of the reactant is always greater than the mass of the product. Okay, if what? This only one condition. When this happens, when unstable nucleus become stable, mass will definitely reduce. The mass, when it reduces, the differences in the mass is E equals to mc squared. You know, the differences in the mass, that means the mass of the reactant minus the mass of the product, C squared. This energy will be released. This the energy will be released. Okay, will be released to the surrounding. Okay. So mass of the reactant greater than mass of the product. Which binding energy per nucleon greater? Binding energy per nucleon of the product is greater than the binding energy per nucleon of the reactant. Try to understand this. Okay. If let's say a nuclear reaction, a substance A turned to become B, a nucleus of A turned to become B, and they found B is more massive. They found B is more massive than A. Okay, let's say a reaction now. A turned to become B, nuclear reaction. Okay, but B found to be more massive than A. Tell me, is this process is an exothermic or endothermic? The A turned to become B, and B found to be more massive. Okay, so mass has been increased or decreased. You know, nuclear reaction, mass and energy conserve, right? Mass and energy conserve, right? Conserve, right? Mass together with energy. If from A to B, if mass is increased, means what happened to the energy? Okay, so if mass increase means mass energy need to be supplied. You need to supply energy. Okay, you need to supply energy. So this is going to be an exothermic process. It's going to be an exothermic process. Okay, it's going to be an exothermic process. If a nuclear reaction where the mass is increased means this nuclear reaction going to be an exothermic process. That means sorry, what I'm doing. It's not exothermic, it's endothermic process. It's endothermic. It's an endothermic process. Energy need to be absorbed from the surrounding. Is it beneficial for human? Is it beneficial for human? Is it used for human? A changed to B, but energy is absorbed from the surrounding. It's an endothermic process. Is it useful for us? It's not useful. Why it's not useful? Why we do nuclear reaction? We want to get energy. Okay, we want to get energy. So the naturally occurring process, when A turned to become B, naturally occurring process, the B will become less massive. Okay, the product will become less massive. That energy will be released to the surrounding. Okay, whenever a nuclear process energy is released, you should understand the product is more stable than the reactant. Okay, the product is more stable than the reactant. Okay, guys, so we learned a lot today. Okay, so I stop here. Just recall back what you learned. Okay, so what you learned today? You learned three things. You learn about mass defect. Okay, first you learn about mass defect, and you learn about what is definition for atomic mass unit. Okay, mass of 1/12 of the carbon-12 atom. And you learn about binding energy. Okay, what is binding energy? The amount of energy required to separate all the nucleons from the nucleus to infinite. Okay. Then we talk about something called binding energy per nucleon, which determines the stability of the nucleus. And we found that iron was achieving the most greatest stability because it has the greatest binding energy per nucleon. Okay. So then we talk about fusion and fission. Okay, a little. Okay, so I stop here. So just go and try to read through more. Okay, I'll catch up with you tomorrow. Okay, thanks.
Yes, I have a question.
Yeah.
Why is the binding energy of smaller nucleons bigger than the binding energy of a big nucleus?
Binding energy of the smaller nucleus. No, binding energy of smaller nucleus normally smaller than the big nucleus. What binding energy?
Then just now when you showed the this one, can you scroll us?
Oh, the slide, is it?
No, inside your whiteboard.
Or whiteboard,
Yeah.
Okay.
Yeah, what is the binding energy of the product greater than the binding energy of the reactant?
Okay. Binding energy of the product, Oh, no. What I'm saying is the binding energy per nucleon of the product.
Oh, okay.
Binding energy per nucleon of the product is greater than the binding energy of the reactor, for sure. Yeah. Okay. Any other questions? Angus, okay.
Yeah, okay.
Okay then. Okay, guys, thanks. Those who have questions can stay back. Thanks.